Okay. So let's go. Hi. So as you can see, we will talk about run test for directional data today. So this is a joint work with Christian Franck, Yuchi Goto, and Thomas Verdeblou, which is my chief as a postdoc in ULB. So before going into the run test, let's talk about an application. And we will study the solar sunspot. So here you have a photography of the sun, and you have some sunspots on the surface. Okay, so of course we have more data than this. So it is sorry, a classical data set. Maybe you are used to it. So we have the location of the sunspots according to the time, according to a cycle. A cycle for a sunspot lasts around 11 years. Okay, so the first thing that you can say, we can say, but of course we are in a directional symposium. So directional because on the sphere of dimension p, here the application will be of in dimension 3. And the first thing you can see that the location, according to the time, will have a kind of modelization. It means that at the beginning of the cycle, the point is in red, okay? And at the end of the cycle, all the points are in yellow. You can see that in the beginning of the cycle, you are far away from the equator of the sun. But at the end, we are close to the equator. So there are a feeling that we sense that there is a modelization that we can do, maybe a serial correlation. And when we are looking at this data set, we can see that we have rotationally symmetry around a localization which is a north pole. Okay, so in the following, we'll be in this kind of situation. Sorry. So what can we say about the localization? Actually, there is some bibliography on this, and we will start with the Sporus law. The Sporus law is a description of the location sunspots, but we studied with it the absolute latitude of the sunspots. And with this, we can see that there is a correlation between the absolute latitude. Okay, so you have here the butterfly diagram. Okay, and you can see across, the different cycle, you can see that in the dataset we have a lot of cycle. We will talk about it a little later. So we have this feeling of the correlation between the latitude and the effect of being closer to the equator according to the cycle. But the correlation is for the absolute latitude. We have also an independence for their sign. So you will be independently in the north or in the south of the sun in terms of hemisphere. But the question is, okay, for the latitude, what can we say about the longitude? And can we detect also a dependence? And we will try to detect a serial correlation. Okay. So it will be the goal of this talk. And on the first part, we will talk about the run test in different cases. And after the run test for directional data, and we will introduce the tangent Markov alternative. And we will end with the Monte Carlo and the application on the sunspot before concluding, obviously. So what is the runs? But let's start with the univariate framework. Actually, if you want to test the randomness of a sample x1 until xn, we will suppose that the location parameter of this dataset is theta. We can define the sign of xt, obviously. Okay. So ut will be the sign of my dataset according to the location parameter theta. And if you want to test the randomness, you will define the run. And a run is just, when you have the sign, a consecutive series of observation with the same sign. Okay. And the idea is, if you have total randomness, you will be a kind of Bernoulli of half Bernoulli, positive and negative. Okay. So you can define the runs this way. Okay. And actually, it's an easy example, and we are in the univariate case. You have the limiting Gaussian law, the limiting distribution, which is a Gaussian. Okay, so of course you can construct a test to reject the randomness according if the number of one is too small or too large. So actually, it's a very But the fact is, we are in the univariate case. For the multivariate framework, of course, you do not have the sign anymore. So we will replace the sign ut by the definition of the multivariate sign, which is the sign theta is again a location parameter. So the sign will be xk minus theta divided by theta. Okay. So if you take this definition, you will no
We
longer.
can't hear you. Something is wrong with sound a bit.
Okay. Can you do something else? Can you hear me?
Yeah, it's much better now. Thank you.
Okay, sorry. So when during the ones when we were looking the change of the sign, here we will change the different angle between ut, and ut minus one. Okay, so we define the run on the multivariate case this way. Okay, so you have the same definition almost. So this time you're measuring the angle between ut and ut minus one. And again, you will have the asymptotic normality of this statistics. So you can construct a test for randomness. And the idea is if you are looking the angle between ut and ut minus 1, you will not have randomness if this statistics, the square of this statistic, will be too large. Because in this case, it means that you are counting in one direction. Okay, so you are not random. Okay, but for the directional framework, we all know that we can, when we have a sample of the sphere, xt, r, here, we can always decompose it as two parts. The first part, I will call it Vt here, it's the projected part, and St will be the multivariate sign, okay, and it's the tangent component, okay. Here, gamma theta, which appear, it's the semi-orthogonal matrix, okay. So we will just adapt the run definition with this. We replace ut by the multivariate sign in the directional data, okay. So here you have the definition of R1, okay. So I talked at the beginning with the example that we are looking the case of rotational symmetry. What can we say about the rotational symmetry case? But we know that the density of the rotational symmetry distribution is this way, with an angular function g, okay, and a location parameter theta. Okay. For example, the von Mises distribution is just exponential with a concentration parameter kappa. Okay. In this case, we know that we have the first one, the density of Vt. We know that the tangent part will be uniform on the sphere of the dimension t minus 2, and we will have independence between Vt and St. Okay. So, you have also we will need some assumption of the angular function. Okay. For example, here. Just know that phi g for the von Mises cases, for example, is only kappa. Okay. So, with the rotational symmetry, we have this particularity. And now I would like to introduce the tangent Markov distribution, which will be our alternative. Okay. So we define the tangent Markov distribution by this, considering that the tangent the sign of directional data S1 until Sn has this kind of density. Okay. So here appear a new parameter lambda. Okay. And with this density, first thing, you have that St, the marginal, is still uniform on the sphere of dimension t minus 2. But you will have von Mises distribution for the conditional distribution of St, knowing St minus 1. Okay. So lambda is the concentration parameter of the von Mises distribution, so it's strictly positive. Okay. But in this case, we have the density of the sign, the directional sign, and considering the rotational symmetry case, we can also have the density of everything with Vt and St. Okay, and we can show that the density of this is given by this formula. Okay, so why it is interesting? It means that if we are interested into testing the randomness of the directional sign, okay, so uniformity against tangent Markov distribution, we will infer into the lambda parameter. Because if lambda equals 0, the von Mises distribution for the conditional will be uniform. Okay, so the test of randomness of the ST, so uniform on the sphere of dimension p minus 2, can be resumed, can be just so as this. It means lambda equals 0 against lambda is strictly positive. Okay, so what can we say? So remember that so under the rule, okay, we still have our run statistics, which is defined as this way. Okay, I will just add that here we talk about lag one run because we are looking the angle between st and st minus one. We will talk later about lag h statistics. Okay, we introduce Sn theta, which is the estimator of the variance, okay? And we can show that the asymptotic distribution of the statistics is normal, okay? So considering this, you can construct the test. Actually, you will take the square of this statistic, so you will have a chi-square distribution, okay? But what's happened under the alternative? Under the alternative, we will consider then a perturbation actually of our distribution. So you will have two perturbations. The first one for the lambda parameter, the concentration into the tangent Markov distribution, and a perturbation of the theta parameter, the location parameter. Okay, and we study the log ratio likelihood of the distribution under the alternative against the null. Okay, and we can show that we have a lab result with this, where delta n is a central sequence of for this problem, and this central sequences is a central sequence, sorry, is has two parts. The first one for the lambda parameter, and the second one for the theta parameter, which is defined as delta lambda n. Okay, the first thing that you can see is that the lambda part is proportional to the run statistic that we have defined. Okay. So, and also with this, you have gamma, which is the Fisher information matrix, or the covariance matrix, if you prefer. And you can see that it's this matrix has a diagonal structure. So from this LAN results, we can have a very interesting results is that for the test, lambda equals 0 against lambda strictly positive, the locally and asymptotically most powerful test, we will call it fiat, it will be this test, okay, projecting according to the quantile of the normal distribution. Okay. But as I said, sorry, delta lambda n is proportional to the run test that we classically defined at the beginning of this talk. Okay. And also, there is an important thing that from this LAN results, okay, we can replace theta, which can be unknown, of course, by an estimator as long as it's a root n estimator. Okay, and in this case, there will be no cost asymptotically, and we will show it with the simulation. Okay, and so voilà. So we will be able to make the difference. We will plot the difference between the classical run test and the optimal test field. But here you have the results for lag one. Okay, so you can detect the serial correlation of lag equal to one. But of course, you can want to detect a serial correlation of lag equal to 2, 3, let's say 8. So for this, we will define the run statistics, but for a lag equal to h, okay, which is RHN here. It's obviously the same. Huh? It's just you are looking the angle between ST and ST minus h. Okay. So this time we will define a new statistic, which will be this. Okay, and we are able to show that under the rule, so when ST are uniform and are independently and identically distributed according to the uniform on the sphere SP minus 2, the null, this statistic will be a chi-square distribution with h degrees of freedom. But under the alternative with the perturbation of the lambda parameter, the concentration of the tangent Markov alternative. Okay, you will have again h degrees of freedom t-square distribution, but with a non-centrality parameter. Okay, so now we have we have our statistics, and we have said that for lag equal to 1, we have the optimal statistics, the optimal test. So let's look at the simulation. So phi1, phi2, and phi3 are the classical run test for h equal 1, 2, and 3. And phi opt is in Bordeaux, the color Bordeaux. Okay. And each time you have two lines. The first one for the estimator of theta, and with the other one with the true value of theta. And you can see that, of course, Fiat has the power, has the most important power. And you can see that it's increasing until one when you are going away from the null. Okay. And when n is going large, for n equals 1 for them, you can see that the cost of replacing theta by an estimator of theta, which is root n estimator, has no cost. Okay. So what can we say for our sum? But for the sum, so we take the longitude of actually of the sunspot, okay, because the longitude is the tangent part of the localization of the sunspots, okay, and we applied our test to the sunspot for all the cycles that we had in the data set. Okay, so it started with the cycle 11, sorry, and each time we did 3 tests. The first one on the left, it's our test for the directional, with the directional run test. The second one is the latitude runs, okay, the classic run test. It's a univariate, okay. And the last one on the right is the absolute latitude runs. So you hope to observe the spore flow on the right, okay. So what we see that actually on the left, we always reject the null hypothesis, which means that they have a serial dependence into the longitude. Okay. So for the absolute latitude, we almost reject. Now, you can see that for all the other cycles, that it's almost the case every time, except the cycle 11, okay, which was a long time ago, and we not so much data inside. Maybe it's due to that, okay. And in the middle, you should have independence, independence of the sign, and well, you can see that almost every time you observe it. Okay. So just here you have the last.
You have around 2 minutes.
Yeah, thank you very much. So I'm going to conclude actually. So we define the directional run test, and actually we are able to construct an asymptotically and locally optimal test for this special case with the tangent Markov alternative. The simulation show it's okay, of course, and we have the application with the sunspot. But for the future work, of course, you can see that here we consider in the simulation and dataset h equal to 4 at the maximum. Okay. The question can be what's happened when h is going to infinity. Okay, and actually it's something we are looking at. And voilà. After there is also a possible work into defining a more general case as a tangent Markov distribution with the von Mises. Okay, so why not a rotational symmetry tangent Markov distribution? Voilà. So thank you, everyone. And if you have some question, please feel free to ask.